I'm talking artificial intelligence, machine learning, the difference between them, and how do they actually work. Also showing you a simple visual example with explanations. Stay tuned.
3 separate devices. This is one device.
You associate with people that are better than yourself and act.
I'm going to make him an offer again.
Hey everybody, I'm Sam and this is Antiversal. So today we're talking about artificial intelligence, machine learning, what's the difference between them, how do they actually work, and also give you a simple example that will hopefully show you and give you a better understanding of the different dynamics between it. And first I want to start with the fact that probably if you're not doing machine learning, everything sounds very abstract to you, but I promise you there's nothing abstract about it at all. And it does look complicated at first, but when you get into it, it will just become more and more clear. Everything is based on very fundamental mathematics, but today we won't be caring much about it. It's more about the ideas behind it and why does it work. So first of all, artificial intelligence and machine learning too are big buzzwords, right? Everybody are using them everywhere, but what do they really mean and what's the difference? Well, machine learning is the actual theory and mathematical algorithms that are made in such a way that they learn themselves. So they're not pre-programmed for different states, but they learn based on experience. Artificial intelligence or AI systems are software. They can also include hardware systems like the Android we see here that actually use machine learning, but obviously it's part of the system. So it has a lot of different interfacing, a lot of different mechanics, and machine learning is just part of the system, like the brain, the most important part. With that out of the way, let me talk about why machine learning is actually so important. Well, as you can see, with most of the software that we used in the past, and most of the software we still use, it's based on pre-programmed states, right? So let's imagine that every program has a lot of different states that's in it, and based on its input, it could be your mouse, it could be your keyboard, or based on its internal some kind of results and calculations, it has pre-programmed transition to different states. So all the states are pre-programmed, and based on inputs and outputs, the program itself knows where it has to go. But obviously the problem with that is that if there are too much inputs and too much different variables, it becomes practically impossible to program in all possible combinations and then obviously the states about them. So that's where machine learning comes in. The idea behind it is that we don't program the software beforehand. So if we say we wanted to calculate 3 plus 4, we don't say it's 7, right? So we give it a different kind of calculations, and then based on that training and previous experience, it can tell, okay, now it's 7. And obviously in the beginning, machine learning systems are much worse than their pre-programmed counterparts, right? But the idea is with training and in time, there are actual possibilities to be much better, with much better performance, and obviously doing much more complicated tasks. So why does machine learning and artificial systems become so popular all of a sudden? Well, the truth is that they need, especially for training, very big computational power. So only in the last decade, and especially in the last years, it's actually become feasible, and the computing power has become cheap enough so we can actually, and powerful enough so we can actually use it in practical ways. So to let me just summarize that in a bit, why do we really need machine learning? Well, if we have some kind of program with states, for example, your remote control, that if you click that button, your TV needs to turn on. But if we have a problem like, let me classify an image, right? And an image has a lot of pixels, so every pixel is possibly an argument or a variable or an input, and every input has different features, meaning that one image could have possibly thousands, millions, or even billions of different arguments that can have different values. And then we take into consideration that there are thousands or millions different images, right? And even if we take two photos of the same thing, they won't be the same. So even if we capture, the same bottle of water, the two pictures on a pixel level, they won't be the same. So it's practically impossible to program all the different combinations. So when we give it to a program, it knows what the object actually is. That's where machine learning and artificial intelligence comes into play. So what's the idea behind it? Well, as we can see on all the different pictures, there is a brain. That's basically the idea, because the most advanced AI systems use machine learning called neural networks. The neural networks try to mimic the way we ourselves learn and classify things. That's why they're really good in image classification, in sound classification, and also in some kind of input classification. That's what we use for face detection in your smartphone, or Google for its input of search, right? So if we take into example our vision, right? So we don't really think about, okay, how do I actually recognize what's in front of me? For example, you're looking at a bottle of water. How do you know that the bottle of water is actually a bottle of water, right? So there's some kind of patterns and features about the shape, about, the perceived material. So you actually know that's a bottle. But how can we actually mimic that into software? Well, the answer is with a network of neurons. And again, with our vision, right? So we perceive through our eye the light of the bottle of water. Then in the back of our eyes, the light is transformed into bioelectricity signals, which are transported to our brain through neurons. So you can look at neurons, all these little dots here, as some kind of filters. Input goes into the neuron and then comes out, and what comes out is a little bit changed through the filter into the neuron. So the idea is we get rid of the unmeaningful information that we don't think actually help us understand what we see, and we enhance and keep the meaningful information, or those features and patterns that we believe actually tell us what's in front of us. And then the idea is, by the time that the inputs have come into our brain, the information is changed in such a way that we have harnessed the meaningful patterns and features, and then our brain looks into its database and says, oh, these features have a label of bottle of water, for example, right? So we are seeing bottle of water, and tada, we have it. So the idea is we don't actually reprogram it, but through some kind of changes, we try to get the meaningful information we need. So that's the idea of the machine learning, but I understand that it still sounds very abstract, right? Well, I would like you to think about neurons. It's just kind of, as I said, filters, but what does filter mean? So you have an input, for example, just a number, 2, for example, and we'll look at the neuron is just as a collection of numbers that are called weights. And when we multiply number, the input that comes into the neuron by the weights that are into the neuron, then obviously different numbers comes out of it, which the idea is they have more meaningful information. And as I told, I try to make it as simple as possible. So here on the left, you can see a very simple neural network that's with one hidden layer, it's code. So here we have our inputs. So those are some kind of features. For example, if we have different pictures of numbers, like here, right? So imagine that every number is a different picture. So we would like to make our network, our software, classify every picture. So a picture goes into our software and we would like it to tell us if it's 1, 2, 3 or 4, right? So let's say we have 1, 2, 3 and 4. So for example, here on the output, that's 1, that's 2, that's 3, that's 4. So if it is a 1, here this neuron needs to output 1. And if it's 2, neuron needs to output 1. And if it's not, it outputs 0. So how we can actually make that? Well, we take our image and we strip it down to a bunch of features. So what we have here, it's called the feature matrix. So features, what does features mean? Well, that is just some kind of function of our input. So as we said, images are a collection of pixels, right? So, and every pixel has some kind of value. For example, 10, right? So here our feature can be just 10. So it could be just x. It could be x on the power of 2, so it could be 100, right? It could be some kind of, sign of x or something like that, right? It's just a function of our input variable. And the idea is, no matter what kind of input we have, so no matter what kind of image we have, we can create design matrix that has the same functions as features. So the only thing that changes are the variables themselves. So here, for example, we have 5 features. These 5 features come into our network and they are multiplied in these neurons by some kind of, as we said, they're called weights. And weights, as the name suggests, they try to decide how important a feature is. So for example, here we have a 1. And we have a bunch of features, right? If that was a real network, obviously it would have, for example, 1,000 features for a single image. So we will try to understand how every single feature actually tell us if that is a 1. And obviously, the more important it is, then the bigger weight it needs to have. And then we have different weights in this neuron that will tell us if it's a 2 or it's a 3, it's a 4. So at the end, what we have is a lot of multiplication of different vectors and matrices. And I know here it can get a little bit more complicated with the maths, but the idea is important. The neuron is a filter, and we have an input of features that somehow describe our variable input. And I'll give you a simple example here. So here I have simulated a very simple linear regression. So basically that's the simplest machine learning that you can do. So here, don't mind much of the actual language that it's written, that really doesn't matter. It's more important to get the idea. So here I have a function, right? And it depends on x and n. So those are variables. And n I'll always keep equal to 1, as you can see here. Okay, this is our function, and this is the 1 here, right? And again here. So basically the only variable we have is x. Okay, and that's a function that has the cosine, and here we have x and so on. It doesn't really even matter. So here I make my input. So that will be my input variables, right? For my training set, because we said we need to train our algorithm. And the training, what it does is it decides the weights that we need. So how the features that we receive as input tell us what the actual thing is that we're looking at. That's the most important thing, right? So here I make my input x, right? And here I just make 200 points between -1 and 0, right? So I have 200 points between -1 and 0. So that's minus 0.99, minus 0.98, and so on up to 0. Here I make my labels or results. So I take my function, I put in my training values for x, and I add in some noise, because obviously to make it more real, always it has some kind of noise, so the function is not the same. And here the function, it represents, for example, theoretically said, there is a function of all the pixels that tell us what's in the image, right? But obviously that's very, very complicated and it's very theoretical, right? We don't actually know what the function is. But in order to make a simple example, here we take a function that we know actually what it is, so we can actually make our labels, because the labels are basically the right answers that our machine learning algorithm needs to use to learn. For example, in a more real life situation is for image classification, we have a bunch of images and we want to teach our machine learning algorithm to recognize if the image has a cat in it, right? So we have 10,000 images, all random images, and in there are 1,000 images of cats. So on the all images that have cats, we'll say, okay, that's a cat. And all the images that there aren't cats, we'll say that's not a cat. So those will be our labels in a real life situation. Here, our labels are the actual values of the function with our input variable values. And here I make my input real data set. So that is between -1 and 1 with 400 points. So I train it with values between -1 and 0, and my real data that I would like to make a prediction on will be between -1 and 1. Because at the end, the idea is our machine learning algorithm or AI system to be able to predict results on the base of unseen data. Right? That's the idea, because if it's seen data, we already know what it is. But the idea is all kind of random data that the algorithm hasn't seen, it can predict. So that's why I'll include 0 to 1. Here, I make my actual true values between -1 and 1. So my y's, or my labels, if I actually had to use them. And I do that only so we can verify if our predictions are right or wrong. In real life situation, you don't actually have those, right? You want it to predict. Here, the next step is making our design matrix. So our design matrix is comprised of our features. And here, for every x, for example, -1, so here I have two features for every input x. So I have a 1 and I have the x itself. So for example, for -1, my two features will be 1 and -1. For 0, it will be 1 and 0, and so on. I do a matrix with all my 200 points between -1 and 0 and 200 ones. And that's my training design matrix. So as we said, we are training it on values between -1 and 0. So those are the features for the training set. Here I make my prediction design matrix. So my real values that I want it to make predictions. And as we said, those are between -1 and 1, again with 400 ones. And here is the point where I actually train my algorithm. So what's the training? As we said, is just calculating weights for every feature. As we said, we have only two features here, so we have two weights. How do I calculate the weights? Well, the idea of the weights is that we have some kind of inputs, our design matrix of features, and then we have some kind of outputs. So we'd like to find some kind of, as we said, numbers, right? Weights are just numbers that represent the smallest possible errors from the perfect value. So to make it even simpler is, for example, we have an input of 2, right? And our feature is just the number 2. And then we have our label, which is our y, or our right answer, which is 4. Obviously, in this example, our weight needs to be 2, because 2 multiplied by 2 is 4. Then our next training date is 3. and our label is, for example, 12. So the weight for it should be 3 by 4 is 12, so it should be 4. But as we said, for every feature we have only one weight, so we have to find the optimal weight. What's the optimal weight? Well, it is 3. It has a minimal error from 2 and 4, right? 3 is just in the middle. Obviously, when we have different features, we can have different proportions, and then for the training set, which is, for example, 1,000 different x's, we have to actually find the optimal values. And how is that done? Well, we have something that's called Moore-Penrose inverse matrix, and there is quite a lot of math behind it. But the idea is, when we take that inverse and we multiply it by our labels or our right results answers, we actually get our weight. We get our optimal weight. Then to get our predictions, what we just do is multiply our weights by our prediction input design matrix. And here are the results. And I have marked with red our training labels. And as you can see, they are between -1 and 0. I have marked with yellow my real data right answers. In the real world, we don't actually have that, but here, because we actually know our function, we can show it so we can see if our machine learning algorithm has actually worked or not. And with the blue line is our prediction. So as you can see, it's actually very well trained for our training set. So I would say it's almost exactly in the middle, because there is a noise, right? So we want the exact middle one. Then for our yellow, where this is data that it's not actually trained for, as you can see, it's a little bit in one end, so it's not as accurate, but as we can see, it actually gets the trend and it looks pretty well. We have actually succeeded and trained our very simple machine learning algorithm to recognize data. So now we can input it values from 1 to 2, and it again will be able to recognize them. Here I have different examples where I want to talk about the actual importance of features and the big trade-off between actually making our algorithm very well trained for the training set, so it's actually very well mapped and knows very well how to react on the data that it's seen, and make it generalized so it actually acts very well on general data. But I will talk about that in my second video about machine learning, which should be in the card section in the top right of your screen. I hope you enjoyed this video and learned something interesting. Ask me any questions and stay tuned to Antiversal.